our first lecture covered symmetry operations. The second lecture dealt with point groups. The third lecture focused on crystal systems, the 7 crystal systems, and the 14 gravel lattices. Now we would like to put everything together into space groups. Now the point group is a group of symmetry operations that leaves a point, symmetry operations around a point that leaves a collection of points or a collection of objects, polygons, atoms in an invariant state, which means it connects two conformations that are indistinguishable. It connects two symmetry related configurations. So you do a point operation and the new configuration is identical to the original. Okay, so this is a point operation. And all these point operations can be clubbed together into 32 groups, which are called point groups. Now when you have point groups, a convenient way of looking at the point groups is to bifurcate those point groups into 7 distinct classes, which are called crystal systems: cubic, tetragonal, orthogonal, tetragonal, orthorhombic, triclinic, hexagonal, rhombohedral, monoclinic. There are 7 crystal systems. Then we also looked at the possibility of increasing the number of points per unit cell beyond 1. That led to different kinds of centering. The most basic of them all is primitive. You could have body-centered, you could have face-centered, you could have centering only along one direction, and so on. Okay? And not all kinds of centering are compatible with crystal systems. For example, you cannot have a C-centered cubic. Alright, so we also learned that. Now what we would like to do is, we would like to see that when atoms or molecules combine into 3-dimensional solids, they belong to a particular point group. Now the point group tells you the external form of the crystal. Because point operations are operations about a point. So you take a geometric object, center of the crystal, and do a point operation to which that crystal belongs. The structure of the crystal, the external morphology of the crystal will remain unchanged. But inside the crystal, when you look at the arrangement of the atoms, additional symmetry operations can appear, which have so far been discounted. And those are translational symmetry elements. Point operations do not include any translation whatsoever. They are just operations about a point. A mirror plane is also an operation about a point in disguise, by the way. A mirror operation is can be referred to as 2R. Okay? So there are additional symmetry elements as well, which have so far been discounted. When you include those translational symmetry elements onto the framework of point groups, you get space groups. Now it's easiest to understand space groups when we look at how they develop, and we can pick up one particular example of a space group that will clarify things. So I've given you a few handouts. So on this handout, there are 3 columns. There's a crystal system, a point group, and space groups. So you already know that there are those 7 crystal systems. Okay, so that's clear. And you already know that there are certain point groups that belong to certain crystal systems. Crystal systems are demarcated according to the shape of the unit cell. So the symmetry operations in the point group necessitate that the unit cell has a particular shape. And that's why you can club together the different kinds of point groups into a crystal system. Correct? So you have crystal systems, the 7 crystal systems, and a collection of point groups. For example, triclinic just has either a 1 or a 1 bar. Monoclinic has a single 2-foot axis, a single mirror plane, or a two-fold axis and a perpendicular middle plane. Orthorhombic has at least two two-fold axes of rotation that are mutually perpendicular, or two mirror planes that are mutually perpendicular. Tetragonal necessarily has a four-fold, four or a four-bar axis. Trigonal, so so they have actually clubbed together hexagonal and rhombohedral here. So hexagonal has a 6 or a 6-bar axis, and rhombohedral has a 3 axis that is along the body diagonal. Okay, and a 3-bar axis that is along the body diagonal. And a cubic has a 3-fold or a 3-bar axis along the body diagonal. Okay, so we've already seen this crystal system and the point groups. Now in the last column you can see space groups. For example, if you look at triclinic, point group number 1, there's one space group associated with it, which is P1. And I'll explain what these space groups mean. Okay? With the point group 1 bar, there is only one space group associated with P1 bar. I'll explain what it means. With monoclinic, the point group 2 or C2, there are 3 space groups associated: P2, P21, and C2. Alright? So the difference between P2 and P21 is that P2 is primitive, it has a 2-fold axis of rotation. P21 is also a primitive lattice, but instead of a 2-fold axis of rotation, it has a screw rotation, a 2-fold screw rotation. And we're going to learn what that means. C2 is a centered monoclinic lattice with a 2-fold rotation, and so on. So the number of space groups associated with just one point group 2 is 3 for this monoclinic case. Okay, so now what we would like to do is we'd like to kind of understand all of this. So let's begin with one example. So if you turn to there is another sheet that I have provided, which is a set of 3 leaves. On the top left it's written PMM2. Okay? So we're going to consider this space group PMM2 and see how it develops and what it means. First of all, let's talk about the point group C2P, whose international notation is MM2. This is a point group. This is a collection of atoms or a collection of objects, polygons, or even a lattice which belongs to this point group. Now, if I would like to draw the stereographic projection to represent this group, can anyone indicate what this projection is going to look like? If I were to draw a diagram that represents a point group MM2 arrangement of atoms, what will this diagram look like? I take an arbitrary object to start. This is above the plane. First of all, I can draw C2. C2 is a 2-fold axis of rotation over here. This leads to, so this is a 2-fold axis of rotation. It gives me a point over here. Correct? C2B is a C2 cyclic rotation and followed by vertical mirror plane. So this is my vertical mirror plane. This object will be reflected here. I get a comma here with a plus sign. This object is going to be reflected here. I get a comma here with a plus sign. Okay? So this 2-fold axis of rotation and a vertical mirror plane has automatically resulted in another mirror plane. So this is the nomenclature of this point group, MM2. 2. And we already know that this belongs to the orthonormic class because there are two mutually intersecting mirror planes. By definition, if you would draw a unit cell which has the same symmetry elements, we could draw an orthonormically shaped cell. 3 angles, each one of them 90 degrees, and 3 different sides, A, B, C, is they're unequal, right? So this is what we've already seen when we develop point groups, right? So this is the collection of atoms that we have. And if you look at the nomenclature here, MM2, for orthonormic, all 3 axes are different. A, B, C are different. So the first letter tells you that there is a mirror plane perpendicular to the x-axis. This one. The second index tells you that there is a mirror plane perpendicular to the y-axis. This one. And the third index tells you that there is a two-fold axial rotation along the z-axis. Okay, so the nomenclature for identifying the, even though it's complicated, is slightly systematic. So this is how this point group is named, MM2. Okay, old notation C2B. Schwann-Frei's notation, the Hermann-Langley notation. Alright, so this is the point group. Now what we would like to do is we would like to connect this collection of objects which has a point group MM2 with a lattice which is orthonormic. So the point group is of the orthonormic class, and now we would like to put this collection of atoms on an orthonormic lattice. Okay, so the motif is an orthonormic point group, and we want to put this motif on an orthonormic lattice. तो हर lattice point एक motif होगा ना, एक collection of objects होगा. Yes, please. C2B is formed by C2, and then you do vertical mirror planes. C2 gives you these 2 points, and then you put vertical mirror plane here to get these mirror images, right? But this has automatically created this mirror plane as well.
Okay, automatic now, that we would have done it ourselves.
We would have done it ourselves, then you would have a diametral point group. But this is a non-essential mirror plane which has been created. So whenever you have a mirror plane that is vertical and a two-fold axial rotation that lies in the mirror plane, you automatically create another mirror plane. Okay? So this mirror plane is generated by the error symmetry operations. Alright, so now let's draw an orthonormic crystal lattice. Now that actually there are 4 kinds of orthonormic lattices. If you do the centering, there are 4 Bravais lattices associated with orthonormic. There is the P, there is the I, there is the F, there is the C. So you could have 4 kinds of centering. No centering at all, primitive, body-centered, face-centered, and C-centered. Correct? The orthonormic crystal system has the most Bravais lattices. So let's consider, for simplicity, the primitive orthonormic. So what that means, I would like to take an orthonormic unit cell. And primitive means there are points only on the vertices. So let's call this the A-axis, the B-axis, the C-axis. So this is my origin. This is my choice of origin for pedagogical purposes. Okay? All 3 sides can be different, but both the angles are 90 degrees. So I take this object and place it here. So if this were kind of this, I just put this object over here and place my objects at these points, right? Since it's a primitive unit cell, there is 1 point per unit cell. Because if I just need to define 1 point, all other points naturally flow out of the definition of the lattice. It's translationally invariant. If I have a point, I advance by UA plus BB plus BB plus WC, I'll get another lattice point. By definition, where UB and W are integers. So I just need to define one point. But the point itself is now occupied by this object, this motif that has MM2, that has an MM2 point group. Okay? So now there are different ways to draw this. And on this page that I have for you, in fact, this is one page from the International Tables of Crystallography, the International Tables for Crystals, Volume A, which has, it's an encyclopedia of space groups, and all 230 space groups that can be formed in 3 dimensions are described in this compendium. So this is one page from this space group. And you can see that there are four diagrams. Alright? So since the orthorhombic system is, you can look at the orthorhombic system, since the ABC axes are different, you can look at it from 3 different projections. And all 3 projections will be different. So you can look at this from the top, you can look at this from this side or this side. 3 projections are possible. So that's why there are 3 diagrams. 2 at the top and 1 at the bottom row left. And I'll explain what the bottom row right means. Okay? So there are 3 kind of diagrams. There are 3 ways to look at it. And all 3 are distinct. If you were dealing with, say, tetragonal, you wouldn't need these 3 projections, because A and B are doing the same over there. So AC projection is the same as the BC projection. Anyway, so first of all, let me kind of view along the z-axis. The z-axis is also called the c-axis. Let me view along the c-axis and draw projection when viewed along the z-axis. ठीक है, थोड़ा सा complicated एक दफा आपको समझ आ जाए. You'll be some of the very few people in the world who actually know this. So if I view from the top, right? So this is my origin. Say this is my a-axis. This is my b-axis. Okay. So I'm viewing from the top. So this is viewing along z. Along C or Z. I'll explain directions later, but this view is along the Z-axis. So I'll explain directions and distance structures later. They're very important. So now I place this motif, this object, which has MM2 symmetry and MM2 point group at this point. Okay. So, all of them are positive, comma here and comma here. Correct? Now, since all of these points are equivalent, they are related by symmetry transformation. That symmetry transformation is simply the lattice translation. All of these points must be the same. And there are only points at the edges, by the way. There's no centering. So I need to repeat this motif here, here, and here. Got it? क्या हुआ है? ठीक है? So I repeat this motif at these 4 locations.
Sir, how will they be oriented, like with respect to each other? Like हम comma फिर भी उसी तरह like करेंगे या
क्या मतलब समझ नहीं आ रहा.
like यहाँ जैसे ये अभी आप कर रहे हैं तो comma फिर भी इसके diagonal पर ही आएगा.
ऐसी तरह होगा ना बिल्कुल. So you do a translation by A units along this system. This entire system moves here by A units. This entire system can move here by B units. Another A units. So it's a translation by A, B, C, 2A, 2B, 3B, and so on. So this is a projected view of this. Later, this is a projection. This is we're developing space group here. So now, if we look at this projection, what we notice is we have certain symmetry elements that have been created. First of all, there is, so if I just hypothetically divide this rectangle into 4 parts, it's a rectangle because it's orthonormic. There is a 2-fold axis of rotation here along the z-axis, isn't it? Which connects this point to this point, this point to this point, and so on. Likewise for all of the points. There is a 2-fold axis of rotation here. Connects this point to this point, this point to this point, this point to this point, and so on, right? 2-fold axis of rotation here, 2-fold axis of rotation here, here. Of course, there is a 2-fold axis of rotation here as well. Okay, any other 2-fold axis of rotation?
So it's pretty easy.
Okay? Got it? So these 2-fold axes of rotation have been created. Any other symmetry elements? So far we have not included any translation beyond the trivial lattice translation. Okay? We just combining the point group with the Bravais lattice. We're developing a space group. Okay? So any other symmetry operations that have been created that you can see over here, yes? Any mirror planes? Okay. This is one mirror plane. Another mirror plane. Great. Mirror plane. Mirror plane. Of course, these are mirror planes. This is a mirror plane. This has to be mirror plane by translation symmetry. Okay, so these mirror planes are also created. Now, this collection of symmetry elements in 3D gives rise to a group of symmetry operations, which has formed by the combination of a point group MM2 onto a primitive Bravais lattice. This new space, this creates a space group. This space group is called, the international symbol for the space group is PMM2, which in this particular case represents the MM2 point group combined with a primitive lattice. MM2 already tells us that this is orthonormic. So this is an orthonormic space group. Okay, so likewise you can have CMM2, we will discuss that in a minute. So this is how this point group is formed. So this is the complete international name for this space group, PMM2. P is primitive, MM2 tells us that it's an orthonormic space group. If for easy identification, it's also given a number. The number is 25. There are 230 space groups. This is number 25. Its old symbol is, now C2B is the point group and C2B superscript 1. There could be C2B superscript 2 as well, C2B superscript 3 as well. This is an old notation and I think there is no systematic way of understanding this, but this is the proper name for this Okay, so there are three figures. Top row gives you the view along the z-axis, the view along the b-axis, and the view along the a-axis in the same order. And the bottom right is what I've drawn. This is how the objects are presented on this diagram. Alright? Any questions about this? And we're going to explain to the other entries in this space group page as well. Because we really want to put atoms into this system. Atoms into the structure. Yes, please.
सर आप कह रहे थे primitive आप वो वाला
क्या?
आप कह रहे कि ये primitive space है आप explain कर
Primitive because it's a primitive lattice. The gravel lattice is primitive, which means it only has points on the vertices. That's for a primitive unit cell. And there's only one point per primitive unit cell. Okay? Yes, please.
So यहाँ पे ये arrow है,
Okay. If you look at the second diagram, the top right diagram, I'm just responding to a question over here. So the thick yellow lines represent mirror planes that are coming out of the plane of the blackboard, and these pear-shaped icons represent two-fold axes coming out of the plane. Now, in this diagram that you see on the right, you have a diagram of this kind, which is a projection along another axis. So this is the origin, they've identified the origin A, and here is C. Okay? So there's an arrow here, an arrow here, and an arrow here, arrow here. And remember, it's an arrow, complete arrow. It's not a half arrow, complete arrow. Arrow here, arrow here. And then there is this angular icon at the top as well. And then these are these thick lines. What this means is that along this projection, the mirror plane here, and a mirror plane here. Okay? And there's a two-fold axis of rotation in the plane of the blackboard. Two-fold axis of rotation here, two-fold axis of rotation here, two-fold axis, two-fold, right? And this represents a mirror plane in the plane of the blackboard. So there's a mirror plane in the plane of the blackboard and three mirror planes or two mirror planes per unit cell, this one and this one, that are vertical. And this is, by the way, CA. So if I were to draw a diagram of the orthorhombic cell, A, B, and C. So this is this thing. So AC has this is a mirror plane, the back at the back, and there is a mirror plane here. These are the two mirror planes that I've drawn. And then there's a two-fold axis of rotation along C, which is, this is a two-fold axis of rotation. This is a two-fold axis of rotation. Right? And of course, this is a two-fold axis of rotation. Okay? So that's what this means. For this particular space group, now crystal structure may belong to a particular space group. There are certain crystals that will belong to the BMM2 space group, that will be of this kind, which will have this combination of symmetry elements in 3D. So likewise, the bottom right has a projection along a different axis. Now, origin. So the next entry is origin. So this description. So where is the origin? The origin is on MM2. The origin of our system lies on the intersection of an n plane and another n plane. The both of them are perpendicular and a two-fold axial rotation. So that's what this means. Origin is on MM2. It's on the intersection of two mirror planes, one along A, one along B, and a two-fold axial rotation along C. That's where the origin is, and the subsequent coordinates are defined according to this origin on this page. Now, the asymmetric unit. Now, the asymmetric unit is a region in the unit cell. There are certain symmetry operations. The asymmetric unit, ASU, is that region in the unit cell within which there is no symmetry element. So all the symmetry elements are on its outside it. So that all the symmetry elements in this space group act on the asymmetry unit to reproduce the entire contents of the unit cell. Okay? So what this means, so they have defined the asymmetric unit for this space group. Now everything is really, really neat here and very systematic. They have defined the asymmetric unit, the locus for points that form the asymmetric unit. X is less than half, Y is less than half, and Z is anything. So this half means, so when we talk about coordinates in crystallography, in crystal structure, we really talking about, by the way, fractional coordinates. For example, x equals 1/2 really means A over 2. A is the length along the a-axis. X equals 3/4 means 3a/4. So everything is referred to with respect to the edge length of the unit cell. That's what is about fractional coordinates. Okay? So according to this formalism, in the PMM2 group, the asymmetric unit, so this point is x equals half, y equals 0, and z equals 0 if you are in the plane. So this entire sector is x less than half, y is less than half, and if you take this to come out and span the entire z height, that will give us the asymmetric unit. And then if you take this volume, this sub-volume inside the unit cell, and you apply any of these symmetry elements, all of these symmetry elements, you will generate the entire contents of the unit cell, the entire crystal structure inside the unit cell. Okay? So this is what the asymmetric unit means.
So why call it asymmetric?
Because there is no symmetry inside it.
Because उसके
There is
साथ-
no, if you notice, there is no rotation axis, roto translation axis inside it. There is no roto inversion axis inside it. There is no mirror plane inside it. There is no point symmetry operation inside this asymmetric unit. Okay? So this is the asymmetric unit. And if I were to look at this in 3D, so the asymmetric unit would, so if I draw the orthonormative unit cell again, then the So this kind of obloid or this cuboid, which is 1/4 of the volume of this unit cell, will be the asymmetric unit. Okay, and all the symmetry operations that exist for this space group will reproduce the contents of this asymmetric unit. Whatever kind of combination of atoms are there inside. Okay. Now, any questions? Yes, please. Hmm? प्लस ही रहेगा ना अगर ये मिरर प्लेन है इसका मिरर इमेज ये है इसका मिरर इमेज ये है नहीं इसका मिरर इमेज इसका कॉमा है तो इसका विदाउट कॉमा ये क्योंकि मिरर इमेज जब लेते हैं तो वो डायमंड बन जाता है कायरल कॉमन पार्ट बनता है ठीक है now comes the next entry is symmetry operations what symmetry operations exist in this PMM2 space group. The first symmetry operation is one, trivial, nothing. The second symmetry operation is a two-fold axis of rotation. Where is that? Along 0, 0, Z, which is now I'm going to identify the symmetry operations. This is my orthonomic cell, unit cell, with the particular motif, right? Don't forget that. You can draw different kind of space using the orthonomic. So with this particular motif, in the PMM2 group, one symmetry operation is just one, do nothing. The second symmetry operation is two-fold axis rotation on 0, 0, Z, which is this line. Correct? Got it? So this is a two-fold axis of rotation. All of the four edges will be two-fold axis of rotation because they're just related by trivial lattice transmissions. The third element is a mirror plane at x 0 Z. What is that plane? This plane. This is a mirror plane M at x, any x, y must be 0, any. So these are the fractional coordinates in which x and z are running variables. So this is this plane over here. That's one symmetry element. And the fourth one is a mirror plane around 0, y, z, where x is 0, which means you take this face at the back. So these are the basic symmetry elements, and all others.
Why don't they take this axis of rotation inside the cell? जैसे हम वहाँ पे बनाए वहाँ तो दो नोटिस के दरमियान ही भी
Okay, let me complete. So now what's going to happen is that these are the basic symmetry operations. Now on top of that symmetry operations, you have additional generators, which will generate all the symmetry operations inside this space group. Now those generators are, one is do nothing, so you do nothing on these symmetry elements. The second is you do a translation 1 0 0, a translation of all of this by 1 unit along the a-axis. That will make the front face a mirror plane, and this will make this axis also a 2-fold axis of rotation. You can also have a translation along of 1 unit along the y-axis, translation of 1 unit along z-axis. Finally, you could have number 2 as a generator. So number 2 is a 2-fold axis of rotation. So you can do a 2-fold axis of rotation for all the basic symmetry elements. You rotate about this axis, you get the other faces. Alright. You could also do a mirror plane along x, 0 and you could do the symmetry operation number 2, which is a 2-fold axis of rotation. You could do a symmetry operation 3, which is a mirror plane x, 0, z, any x. This will generate all the symmetry operations that exist inside this space group.
और सर एक्स वाई जीरो की नहीं हो सकता
कौन सा गलती है?
जो एक है कि मिरर एक्स जीरो जी और फिर एक है जीरो वाई जी में मिरर
इस स्पेस ग्रुप में वो symmetry element एग्जिस्ट करता है. Translation by this vector 0 0 1 1 0 0. 2 means the symmetry operation that has been prior defined. So generator selected, semicolon के बाद जो 2 नजर आ रहा है, second last entry is the symmetry operation that has been defined earlier, which is a 2-fold axis of rotation. So if you look at the asymmetric unit and you look at the edges of the asymmetric unit, these generators will, what these generators are going to do is, look, this point, this symmetry axis, what will do to this asymmetric unit? This will do a rotation about, and you'll get in the unit cell that is behind this, you'll get this cuboid. Okay? When this cuboid is translated to the translation vectors, you're actually filling up this section of the unit cell. Correct? So that has created another 2-fold axis of rotation at this intersection. So once you define the asymmetric unit together with the symmetry operations and all the generators, you'll get all the additional symmetry elements. Okay. Now, really, the most important part which crystallographers use and which is really important when we study crystal structures are these positions. अभी तक समझ आ गई? Now, if we look at the positions, and so there are 2 columns. One column represents multiplicity, Wyckoff ladder, and side symmetry. The other column represents the coordinates. First of all, at the top row of this positional table, you have what we call the general coordinates. So let me write down this table. general coordinates for I. So this symbolism is called, this combination of letters is called Wyckoff position, and I'll explain what all of these letters mean. And I have, since I have a 4 here, I need 4 points. I write X, Y, Z. Point number 1, point number 2. So X, Y, Z is an arbitrary point inside the unit cell. What is that point? Suppose I consider this point X, Y, Z, which is at some distance X along this axis, some distance Y, and at a height Z. Okay? Now X and Y, the position, fractional coordinates X and Y are clear from the diagram. अगर ये पॉइंट यहाँ होता तो x की वैल्यू हाफ होती, अगर ये पॉइंट यहाँ होता तो x की हाफ होता, y की हाफ होता. ठीक है? So the x y position is clear from the diagram. The z position is not. So generally we would more like to write the elevation of these atoms, of these points, write a small fractional coordinate on the z axis. But generally, arbitrary point, you take any arbitrary point x, y, z. Now with the symmetry elements that are present in the P, M and 2 space group, this point group must have equivalent symmetry related points. What are those points? Those points are actually these 4 points. So if this must exist, and this is the P, M and 2 space group, then these 3 points must also exist along with it. Otherwise you do not have the P, M and 2 space group. Correct? So if this is one point, the other point must be, you have this point, this, you must have a point over here. X bar y z. X bar means is shorthand for minus x. You must have x bar y z. You must also have x y bar z. And you must also have x bar y bar z. Correct? Now you can have atoms. If you have an atom here at x, y, z, then x, y, z is totally arbitrary. You must have the same atom, the same chemical identity, the same atom at all 4 of these locations. Otherwise, this structure will not belong to P and P. Okay, it will not obey the symmetry that is mandated for the P and M2 space group. So now this, I can now tell what these symbols mean. 4 means that this position, we have defined the general position x, y, z as multiplicity 4. 4 locations must coexist. So the multiplicity is 4 for this general position. And the symmetry that exists at this particular point is 1. With these 4 points, no additional symmetry is needed. These 4 points, no additional symmetry element needs to be defined. Then just take those 4 points and put them here. Yes, please.
So is this 4 coming from how many unit cells are sharing a point? Because that would give us the number of how many objects.
Not necessarily. Not necessarily. There could be more as well. This I is just a general number because this number starts from A, B, C, D, E, F, G, H, I. It just ends up at I. Okay? And this is the least, this point, this position has the least symmetry. This general point has the least symmetry. So it has the biggest letter in that space group. This letter is called the Wyckoff letter. Okay? The position of these 4 atoms is generally called the 4i position in the PMM group. So if an atom exists on these 4 locations, there must be the same atom that exists on these 4 locations. So you say that the atom is on the 4I bifurcation. Okay. So this is the most general element in this space group. Now let's move on to a few more. Any questions? Let's move on to the next row. The next row says 2H and M dot dot. Let's look at the points. Half YZ half Y bar Z. Now what does this mean? If there is an atom at half YZ, so these are the general coordinates for any atom. Every space group has the general coordinates, which has Z, just the trivial symmetry. An atom place there just has a trivial symmetry. At that point, only the trivial symmetry exists. So you can put any motif, which really means you can put any motif you like, any shape of the motif, any structure that you like, any collection of atoms with no symmetry at all, perhaps, or any symmetry you like at this position. It has no symmetry constraints on the general position. But you need a large number of points there because you have to respect the overall symmetry of that space. So this has this particular position, this is the positional symmetry, site symmetry as it is called. It's called the site symmetry, is trivial. The site symmetry of the general point is trivial. Now you have 2 points. Let's consider these points, half by Z, half by Z on this diagram. Let me redraw the diagram here. Half by Z x, where this position x is equal to half, y is anything. So this could be anywhere and could be anywhere along the z-axis. So any point on this mirror plane. Now if there is any point on this mirror plane, this entire mirror plane, then by the symmetry constraints of this space group, there has to be a point at half minus y z, right? Because if there is, say, some atom over here, this is x half, y is anything, this is our y, and z is anywhere on this perpendicular plane. Then associated with this point, there has to be another point which is at half y bar z, which is really a point over here. So let me actually redraw a new diagram to illustrate this. क्यों हमें चाहिए कि वो मिरर प्लेन है ना, ये देखो. This is one unit cell. Sometimes when you try to understand these positions, you have to draw a neighboring unit cell. So this is one unit cell. Let me draw a neighboring unit cell. If I have a point over here, some atom over here, this has x half, this is my a-axis, my b-axis, and my c-axis is out of the plane. This is x equals half, y is arbitrary, any y, and z is arbitrary. I don't have any z whatsoever. I put the elevation to this. Associated with this point, since this is the mirror plane, I've already identified in space to what my symmetry elements are. This is the mirror plane. I must have an equivalent point over here. Correct? And what is it has the same x, the same z, but its coordinates are minus 1. Okay? So I can displace this by b units. So this, associated with this point, I'll have a point, I must have a point which is this one, which is over here. This this is after translating this point by B units. I can put everything back into the unit cell as well. Okay, nevertheless, associated with this point, I must have a corresponding atom here as well. And since these are atoms, overall atoms, I don't really care about whether they have a comma or not, because just one atom, the mirror image of one atom is just the atom itself. I'm assuming that the atom is spherically symmetric. There is no chirality associated with it. So, correct? So if there is an atom here, there must be an atom here which is the same as saying there must be an atom over here. If this is y, then there must be an atom at b minus y, in other words. Right? The b is the length along this axis. So now let's look at this notation. The multiplicity of this position is 2, and the h is just a Wyckoff letter, the one that comes before I, because it comes down all the way, it starts from A, B, C, D, E, F, G, H, I. On this particular case, it goes to the I. And the associated side symmetry at this point is this mirror plane. This mirror plane along one axis. Okay? And there is nothing on other two directions. So mirror plane along one direction, along the A direction, along the X direction. There is a mirror plane parallel to the X axis. That's why you put an M here. And then you don't need any additional symmetry elements along the y-axis or the z-axis. You put dots. So the side symmetry for this position, for the 2A position, is M dot dot. Right? So likewise, you can construct all the positions that are available to atoms in the P and M group. You can have 2G, 2F, 2E, 1D, 1C, 1B, 1M, 1A, and so on. So let's look at 1A. 1A is just a line, 0, 0, 0. So this line over here, this line, all the points on this line, you can have any point on this line and it does not need another point to go with it. Because this is a special position. Right? All of the other positions are special positions because these two positions are related by symmetry operations. This line is itself on a symmetry operation, so it does not need to be connected with any other point. So its multiplicity is 1. Right? And its Wyckoff symbol is A, which everything starts from A. And on this symmetry element, there are two mirror planes mutually perpendicular and two pole axis equation. So the side symmetry for this axis, which is the 0, 0, z axis, is another position. So you can have an atom anywhere on this line, and it need not have a companion. So the symmetry is the lowest over here, right? Sorry, the symmetry is the highest over here, and the multiplicity is just 1. The entire line has an intersection of two mirror planes, one two pole axis, so exceptional symmetry over here. The full symmetry of the space group is evident on this special position, on the 1A position, which means that you do not, if a point lies on this special position, it need not have a counterpart or a companion.
आपका ही counterpart है
Okay? So these are all the positions. And if you are interested, the final section on this diagram is symmetry of special projections. Really means that if you project, so in the symmetry of special projections, observe that there are 3 projections along 0, 0, 1, along 1, 0, 0, along 0, 1, 0. So you can project along x, y, or z axis, and they are distinct because it's an orthonormic parallel axis. And when you project along x, y, or z, you get 2-dimensional space groups. And they have their own classification. In 3D, there are 230 space groups. In 2D, there are 17 2-dimensional space groups. So it talks about those 2-dimensional space groups. It's not of our concern here, but this is how this table is built. So this is one entry in the international tables for crystallography volume 3. Yes, please.
सर जो उस डायग्राम में आपने साइड की रखी थी वो दोबारा से
कौन सी बिल? इसमें
यस लाइक मिरर प्लेन है
मिरर प्लेन है ना,
यस
तो उसने इस पॉइंट को यहाँ ले गया, तो ये पॉइंट एग्जिस्ट करना चाहिए इसके साथ। अगर पॉइंट हाफ बाय जी पे है तो मस्ट हैव पॉइंट हाफ बाय बार जी।
मेरा सर क्वेश्चन
वो क्यों है? क्योंकि ये मिरर प्लेन यहाँ पे है। तो इस पोजीशन के साथ एसोसिएटेड, ये जो इस पोजीशन के साथ एसोसिएटेड जो साइड सिमेट्री है, साइड पे जो सिमेट्री एलिमेंट है वो मिरर प्लेन, क्योंकि इन दोनों पॉइंट्स को ये वाली सिमेट्री ऑपरेशन कनेक्ट करती है। यस
So you have half G is to recover the symmetry point.
हाफ
Half G. So 1D and second
1D
so लेकिन half of G में तो अगर हम इस specific point को लें तो इससे हम ड्रॉ करते हैं तो यहाँ पे हम half of G पे अगर कोई point ड्रॉ करें तो it has a minus symmetry point.
So if you are looking at this axis over here, so considering this axis, right, this is half G, and this is your 2D position, right? So this point, what symmetry, what counterpart does it have? Here? But that's the same as this, because this is exactly in the middle. So this is connected to this by unit translation vector. So unit translation vectors are excluded from the symmetry operation because we know that this is a crystal lattice and this must be there.
Also sir हम constant numbers को तो change नहीं करें, हम variables को देखें ना, half half को minus नहीं करें, जैसे हम like x y z को ही बदल दें।
Half of something is equal to minus half. Alright, so this is our PMM2 group. So if I were to look at the same point group, by the way, what we've done is we've taken a point group without any translation symmetry elements and put it on a Bragg lattice. In this manner, 73 space groups can be constructed, which do not have any translational element, any other non-essential translational element in them. No screw axes, no glide planes. I'll talk about those. Let's look at another example, the CMM2 group. Now the CMM2 group, example number 2, CMM2 group, the same point group, MM2 group is now juxtaposed onto a C-centered orthonormic axis. So instead of a primitive orthonormic lattice, I now have a C-centered orthonormic lattice, which is centered on its base. So there are 4 points here. Of course, there will be 4 points here. This is my A-axis, B-axis, and again looking from the top, it's orthonormic. Now, since it's a C-centered Bragg lattice, I also have the base which is now centered. The same model is replicated over here. The plus with everything, right? Just keep that in mind. Plus with everything. So of course there are the symmetry elements still exist. So you have mirror plane here, mirror plane here, mirror plane here, mirror plane here, here, here. You have two-fold axes of rotation as well. But now you have additional two-fold axis of rotation. You have a two-fold axis of rotation here, a two-fold axis of rotation here, here, here. Any more? That's it. Got it? So you get additional symmetry elements, and in fact, okay. But another interesting observation. So that's all. You get additional symmetry elements. Another interesting observation is that these additional two-fold axes of rotation create in the process additional planes. So if I were to take a mirror plane, assume I take a mirror plane out of the plane of the paper. Let me draw one. So mirror plane over here. It's dashed. It's coming out of the plane. Correct? Now if I reflect this object, and this object will come here. Correct? The entire object will come here. And then I translate parallel to the mirror plane in the B direction by half units. So I do a reflection on this plane, followed by translation parallel to the plane. So this point is this motive is connected to this motive. Precisely. So there is a symmetry operation that you can apply with this mirror plane. It has a special property. It's not just a mirror plane, it does a mirror operation, a reflection followed by translation. Likewise, this is another such plane. And this is another such plane. Here, and here, and here, and here. So these additional planes are created, and they're more than mirror planes. They're mirror planes coupled with the translation. These are called glide planes. And they come out because we have this additional two-fold axis of rotation in the middle. And in fact, these glide planes are already shown on the. This is not a glide plane. There's no glide plane over here. It's just a mirror plane. No, and there's no. So this is one glide plane. This is another glide plane. There's a glide plane over here and a glide plane over here. Okay. And these are non-essential glide planes, which means they just pop out of this additional symmetry operation, two-fold axis of rotation. So you can. These glide planes are a consequence of this two-fold axis of rotation. So that's why these glide planes are called non-essential glide planes. But there are additional symmetry elements when you consider space group. There are additional symmetry elements. They could be glide planes. Glide planes mean that you can have. So a glide plane, say an A glide plane, really means that you have so this is my A-axis. This is an object over here. This is my unit cell. It's an object over here. A glide plane is you take the image of this about the A-axis and translate by A by 2. You land over here. So this point will reflect back comes here. It gives you point over here. This is called an A glide plane, which is really a mirror plane sigma, since it's parallel to Euler solid sigma A, followed by a translation A by 2. Okay, so this is an old notation for the glide planes. This is called the side notation. You can have a B glide plane. You can have a C glide plane. And a B glide plane. You can have a C glide plane. You can also have an N glide plane. An N glide plane does a translation which is A by 2 plus minus B by 2 or A by 2 plus minus C by 2, A by 2 or B by 2 plus minus C by 2. Right? You can have a translation of this kind on along the phase diagonal. You can also have diamond glide planes. We look at diamond glide planes when we discuss the diamond structure, in which you have A by 2, A by 4 plus minus B by 4, etc. Okay, so you can have additional glide plane. The glide plane really means you do a reflection about a plane and then move parallel to the plane by certain units. Generally, half units or 1 by 4 units. Okay, and they have their own symbols. The glide planes have their own symbols. They can be in different directions and so on. So this additional symmetry element pops out when you introduce translation, and this is only valid for space groups. This is not valid for point. Point groups do not have these translation elements. These are not point symmetry operations. So in addition to glide planes, you can have screw axes. For example, just to give you an example, if I were to take an object, say an object here, right? If this is my object, I rotate it by 90 degrees. So if this is my unit cell. This is the dimensions of my unit cell. I have an object in some orientation. A 4-fold axis of rotation is clear. So if this were a 4-fold axis of rotation, everything would be clear. This would turn by 90 degrees. This would come here, like this. But now, in addition to a rotation by 40 degrees, I move along the length of the axis of rotation by A by 4 or by C by 4 or whatever the length is, by a quarter. So I do this rotation and then I move up by 1 by 4 units. Right? This is 1 by 4 of overall. So this is a 4 by 1 screw rotation. Okay? And then I do another 4 by 1 screw rotation. So this goes to the back, and then I move forward. So this is advances forward but goes towards the back of the black hole. So these 2 points are connected by a 4 by 2 screw axis. A 4 by 2 screw axis is equivalent to a 2-fold rotation. Then I can do it once more. This goes toward this side. Finally, I end up at the same position. This is a 4 by 3 screw axis. So I can have these screw rotations as well. These are roto translations. So I can have 4 by 1, 4 by 2, 4 by 3, 4 by 4, which is just trivial thing. I can have 6 by 1, 6 by 2, 6 by 3, 6 by 4, 6 by 5, and so on. 3 by 1, 3 by 2, and so on. I can have these additional screw rotations. So I can have glide planes and I can have screw rotations. If to the point groups to the point symmetry elements, I include these glide planes and the different kinds of screw axes, then I get not only all the symmetry elements, I can generate all the crystal structures that are known to mankind. All the 230 space groups can be generated. Now, if you look at the CMM2 space group, which is a symmetric space group, you can immediately see that the origin on MM2, you can find out what the symmetric unit is. And notice here that the symmetric unit for this particular case is now not 1/4 of the unit cell, it's just this part. X is less than 1/4, y is less than half, and all of these. So only on its outer edges do you find a proper rotation or a mirror plane. Inside you have glide planes, but that's not a point operation. Okay, so the symmetric unit has reduced. The symmetry operations. Now, the symmetry operations are of two kinds. This is something really important. There are two sets of points. The lattice, since it's C-centered, it has 2 points within the set. One is at the edge 0, 0, 0, and the other is at half, half, 0, which is this point over here. So all the symmetry operations that you want to talk about, number 1, number 2, number 3, number 4, to those symmetry operations, you will get a set that applies here, and you get a set that applies here. So two sets are being written. So let me kind of rephrase this. Symmetry operations for 0, 0 plus set, the symmetry operations are trivial, the two-fold axial rotation, a mirror plane, and another mirror plane. Okay? For the centered point, the symmetry operations are now a translation to the center of the cell, to center of the base, which is T half half 0, a two-fold axis of rotation, which is at one by four Z plus half Z, right? So you need to do this. So the location of the symmetry element number 2 in the centered set is this 3 by 4 Z. So this symmetry operation has an offset. That offset is the location of the centering of that set. Okay? So these are the symmetry operations for CMM2 group. Finally, you have the generators and you have the Wyckoff positions. Exactly the same scheme. But now since it's a centered space group, you need to add, so there are two sets. So you can, there are 4 points in the general coordinates, 1, 2, 3, 4. But the multiplicity that is written is 8, which means you really have 8 points. So you take these 4 points, and to these 4 points you add half, half, 0. So you do an offset along the AB direction by half units each. So you get 8 points in total. And you don't want to write all 8 of them, you just write 4 of them and assume that the other 4 are from an offset, the centering offset from the origin. So you get a multiplicity of 8. So if there's a point on 8F position, there's an atom at 8F position, all 8 of those positions must be fulfilled. Now in the next lecture we'll do more examples of this, and today we're going to post your homework on solid resistance integration. And I'll also upload some resources to read up on all of this.